Hey everybody! How's everybody doing? Radicals and radical functions is what we're going to be talking about today, part 1. We're actually going to only focus in on several of the objectives here today. We're going to find square roots. We're going to sort of approximate roots, but not so much. You can use the calculator for that. That's an approximation. We are not going to look at cube roots today. We are going to look at some n roots, and we're actually going to find the square root, the nth root of any base raised to the n power. And you've already seen graphing the square root function, so we've already seen that in a previous video. So we'll be looking at a couple examples of these to kind of explain things a little bit to help you get started. So remember in our previous video, there are several things that we mentioned for sure. Remember, one of the things that we did mention was that if we take, and you'll see this later, remember I did a very basic one. I said we'll take the square root of a, and that equals a to the half power. Okay? Now, what I'm going to show you today is part of something that we're going to lead into next class, the rational exponents. But I want to show something a little bit here to maybe make things a little bit easier while we work some of the problems out. All right, first things first, let's get started. We're going to do some finding square roots. So I'm obviously going to start with like the easiest one that we have here. I'm going to copy that, and I'm going to bring it down all the way here. I'm going to paste the image, make it a little bigger so we can see it, and then we can work on it. So what do we mean by the square root? Well, if we look at a basic square, and it's a basic square, and we know all sides are the same, it means that we can find area. And area is a two-dimensional space. So when we're talking about area, we're talking about squares for the most part. Okay? Now, when we look at the square root of 25, you might be saying, oh yeah, I know it's 5. Blah, blah, blah. Okay, but be careful. Remember, there's actually an index number. This is called the index number. And we usually hide it in square roots, but it's there. It's 2. So I'm going to rewrite this just so you can see it as the square root of 5 times 5. Now what I want you to pay close attention to is that there is a what? A pair of 5s. That pair of 5s indicates the area. If I go back to my square and I do 5 and 5, you can clearly see the area is 25 because length times width or side times side. So what is the square root returning? It's returning one leg of the area of the square. So what we're actually going to find is that the square root of this is 5 because I have a pair of things and I can take one outside the radical. But there's another problem, isn't there? Because it's not just 5. Aren't there 2 different answers for this? Yeah. Because you're always squaring something, you will always have 2 answers, the positive and the negative. Now that's with squares, and we're going to talk about that in much more detail, which is the square root of 25. Now, I want to take the same problem that we're working on here, and I want to rewrite it a little differently. So I'm going to rewrite the square root of 25 as something else. And remember, I said something like, oh, the square root of a number is that number raised to the half power. So really, this is 25 raised to the half power. Now, this is the key of using these nice little, fractions. See the 2 there? That reminds you of something. That means I need 2 to pull one out. See that? So if I rewrite it as this, then I can see it's 5 times 5 to the half. I need one of the 2, therefore 5, but I know it's an index of 2, meaning it's positive or negative 5. And hopefully this will become a little more clear as we progress through the lesson, or the mini lesson here. Okay, now we're going to take another one, and we'll take a bit of a more difficult one here. Okay, we'll take C. And C, make it a little bigger here, has the square root of 0.04. Now, I know everybody is really a stickler on using decimals, but I'm a pretty big stickler on using fractions, if you haven't noticed. So I'm going to tackle this using fractions, and I'm going to rewrite it as such. What I do know is this. I know that 0.04 is 4 what? Not tenths, but hundredths, right? Okay, that's great. So remember, this is in the tenths, and this is in the hundredths. So what I'm going to do is rewrite it as a fraction, and I'm going to write it as 4 over 100. I'm not going to reduce. I'm going to leave it the way it is. And then I'm going to then I'm just going to put the radical symbol back in place, or the square root symbol back in place. So now we know that this is equal to the square root of 4 over 100. Now, because it's a square root, we can look at it a lot of different ways. You could take this one and take the square root of the top and the square root of the bottom, or the numerator and denominator, respectively. And I'm pretty sure that everybody here knows that we have the square root of 4 is 2 times 2, but I'm going to draw it out, so that's 2 times 2. Oh, with the square root. And that's going to be divided by the square root of 10 times 10, right? So this breaks down to what? I can take one of the 2 2's out, and I can take one of the 2 10's out. So this becomes 2 tenths, or, as we reduce it, 1/5. Is okay? And just because they have a decimal answer, if you actually do see how it's 2 tenths, 0.2. Okay. All right, so we have done a couple of these examples, and I'm hoping that's going to get you started. Now I'd like to look at something with some variables in it, but I want to look at it a different way than what you're going to see, I think. Well, I'll do it this way first. Okay. So here we have g, and we're going to take the square root of it. So, well, this is kind of straightforward in a little, in some ways. And in other ways, it's not so straightforward. And let me show you exactly what I mean. So 16, right? I can write 16 as a product of two numbers, right? It's a perfect square. It's 4 times 4. So I'm going to write 4 times 4. And I notice that x to the 10th has some commonality in it, but you know what? I'm going to actually write all of the x's out, the 10 x's out. And there's a reason I want to do this, so you can sort of see. So this will be x 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So I have all of this junk here, right? Because I'm just trying to remind you about how exponents work as well. I'm going to put the square root symbol back into place. I'm then going to take the square root of 4. I'm going to take the square root of 4 here, and then I'm going to take the square root of all of the other guys left over. So that's 10 of these. Whoops, I should have gone a little further there. Now, what I'm looking for is, you guys already know that the square root of 4 is 2, and you know the square root of 4 is 2. But what do you do with the x's? Now, this is literally the going back to your exponential rules and everything, and breaking it all down. So remember what the square root is. It has an index number of 2. So that means I need 2 of something to pull one out. So there's 1 pair, 2 pair, 3 pair, 4 pair, 5 pair. Oh, okay. Well, that's kind of nice. So that means that from this one, I can get only 1. From this one, I can only get 1. And from this one, I can only get 1. And you see the pattern? Because you're only getting 1 leg back. Now, when you do the multiplication all together, you're going to get 2 times 2 is 4, and x to what power? 1, 2, 3, 4, 5. Oh, well, that's a shocker. Now, you could have written this a little differently. If I take this right here again, and I just make a copy of it right there, and I bring it down a little bit here, so we can work on it again. What I want you to see is something interesting here. You see how there's the 4s that are the perfect squares? Well, watch this. Can I say this? Is this acceptable? See what I mean? How many x to the 5ths do I have? 2. How do I know that x to the 10th is x to the 5th times x to the 5th? Well, that goes back to our exponent rules. X to the 5th times x to the 5th is going to be equal to x to the 5 plus 5, or x to the 10th power. So lots of ways to be looking at these types of problems. All right. Let's actually, we're not going to use the calculator, you can do that, but obviously something like this, 11, is not a perfect square, but it's between a couple of two numbers that are perfect squares. Now, what are perfect squares? 1 squared, 2 squared, 3 squared, 4 squared, blah, 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 blah. But, okay, so 11. Okay, 11 fits between what two numbers? Well, 3 squared, which is 9, so it fits between 3 squared, and it fits between 4 squared. So it's somewhere in between those values, okay? And I can show you a geometric way to actually approximate this later, but for now, you know, it says use a calculator, so yeah. Okay, now finding nth roots. When we look at nth roots, there's something that we need to take into account. So I'm going to just make a little copy here. Oops, make a little copy here. Let's try to, why do I do that? I'm late, it's tired. Switch that, reverse it. Okay, so I'm copying that to bring it down here so we can actually find the nth root. Now, when we're looking for an nth root, some information that might be helpful to you. When we're looking at even roots, okay, even roots, that'd be like 2, 4, 6, and so on. The radicand must be non-negative for the root to be a real number. So if I take an example like the fourth root of 16, well, I'm going to tell you that that's 2. I'm also going to tell you that the sixth root of 64 is also 2. Perhaps you could tell me why. If you look at it very carefully, you'll see why. And let me just bring this out again. So if I carry that same idea of the rational exponents, then I can say a, and I'm taking the nth root of a, then that is really a to the 1/nth power. So what do I mean by that? Well, watch. Ready? And I'm gonna break it down as fast as I can in factorization and show you that way. So I'm going to rewrite this as all factors, and 16 is 4 times 4, so that means 2 times 2 times 2 times 2, right? So that would be 8 times 2, which is 16, all raised to what power? The 4th, right? Because that's the index number. Get it? See it? So how many items of one thing do I need to pull one out? Well, I need 4. And guess how many I have? And that's why it's 2. The same thing can be done with the sixth root of 64. I'll let you do that on your own. But you've got to be a little careful. If I took the fourth root of negative 16, right, then this is not going to lead into a real number. It's not real. And we'll talk about what these numbers are called later. Likewise, if I did take the sixth root of negative 64, because it is 2, it would be negative 2, but that doesn't really make any sense. So, not real. And you'll see what we're talking about later. Now, if I'm looking at, so these are evens. If I make a little note here, this is even index numbers. Okay. Now let's look at some odd index numbers. And the odds can be any real number, which is really, really, really kind of nice. So if I took the cubed root, for example, and we're not going to really talk about it, but I hope you understand the concept of it by now. The cubed root of 64 is going to be 4. And what's nice about it is that the cubed root of negative 64, will also be -4, which is really nice. It's a nice real number. So this means that we can use all real numbers. Okay, let's try another one real quick. So the fifth root of 32 is equal to 2. Well, the fifth root of -32 actually has a real number. It's 2, but it's going to be what? Negative. You got it. Okay, so this is when we have an odd index number. Okay? And that's how you find an nth root. So I'm going to skip over doing a specific example of an nth root except for one, and I'm going to do for G. So let's do for G here. Oh, I forgot to draw my line. That's okay. So here we go. We've got our fourth root of 256 and x to the 12th and, oh boy, y to the 8th. Okay. Now, when you're looking for the nth root, like we said before, we're going to take them individually, and hopefully that will make our job a lot easier. So I'm going to take the fourth root of 256. I'm going to multiply that by the fourth root of x to the 12th. I am then going to multiply that by the fourth root of y to the 8th. And if you see what's actually occurring here, it won't be too bad. One of the things that you should do in this case is kind of rewrite them. But for the time being, let's get started and actually pull this together here. Okay, let's do that. So let's actually just factor this out. I'll do this sort of slowly, I guess, real quick. So 256, it's definitely divisible by 4 because 4 goes into 56. So this is the fourth root of 4 times 64. And that's nice because the fourth root of 4 and 64, well, 4 will go into it, so that's 16 times, and then we have the fourth root of 4 times 4, and then 16 is 4 times 4. So already I'm hoping you can see that we have, how many 4s? 4 of them, and the index number is 4, so I need only one of them. So 4. Now let's take the next one. So we took this one in process, now we'll do this one in process. I'm hoping you kind of see something occurring here that'll make your life a lot easier. But when we factor all of this out, we're going to factor it out slightly differently. So we have the fourth root here of, what would it be if I was, or you were, putting together something that you needed, that needed to be 4 things that are identical that could give you the 12? Let's see, that times that times that times that. Maybe? Maybe? Does that do it? Yeah, right. When you multiply the same bases, you add their exponents. And then how many x cubes do we have? We have 4 of them, which is the index number, which then tells us that we have x cubed. So the fourth root of x to the 12 is x cubed. Let's do the same thing with the last one here. The fourth root of y to the 8th. And let me move that 4 because it looks ugly where it is. And now we're just going to see if we can get 4 things that we can combine to make 8. And I'm pretty sure you already know what we have here. So let's do y squared times y squared times y squared times y squared. Does that give you y to the 8th? Yep. Awesome. Great. And there's how many of them? 4 of them, same as the index. Therefore, we pull only one of them out, we get y squared. So the answer here is 4x cubed y squared. Okay, I'm hoping that helps with the nth roots. And for the time being, that's where we're going to end off with. We're not going to, well, you know what, we might as well. I can give you the concept of objective 5 that you're looking at. But I won't do a problem with it. It's really straightforward, but let's see here. Okay, so now just some information. Okay, and when we want to find, what was it? I think it was A. No, it was. Did they use A's or N's? They used N's. So n, the nth root of A to the n. Now, we used to write it a little differently, but I'm going to make it a little bit easier here for you. When you have this and the case, so I'll have 2 cases here. So if n is positive, so if n is positive, which means that n is greater than 0, right? Then we have the situation that says the nth root of a to the n is equal to the absolute value of a. And then the second case would be, obviously, if n is negative, and that would be if n is less than 0. Then what we have is a nice, easy little formula as well, and that would just give us a. So I'm hoping that this information will help you solve your problems for today. And we're going to get into more depth, but this is just the first step. If you have any questions, please feel free to ask. You can do any of these on your own for self-practice. Note the answers are right here in case you need them and would like to look them over. So hope this helps, and we'll talk in class